Yeah. Okay, thank you. First of all, thank you to Roberto for inviting me here. I'm Dario Peduto from the Department of Civil Engineering of University of Salerno. I'm geotechnical engineering. My presentation will focus mostly on the multi-source database, the risk assessment of roads interacting with slow-moving landslide. This research has been carried out jointly by my research group from University of Salerno and two research centers from the National Research Center in Italy, from IREA in Naples and IRPI in Cosenza. So the topic will be the risk assessment for roads affected by slow-moving landslides. Slow-moving landslides are widespread in different geoenvironmental contexts all over the world. Usually, typical types of slow-moving landslide can be rotational translation slide, earth flow, soil creep, of course, and a combination of them in complex phenomena. They range from the slow to extremely slow types of awareness classification, can occur usually, at least in the environment that I'm going to talk about, in structurally complex formations such as stiff clays, soft clays. And usually the landslides I will talk to you will be usually active landslide moving on existing sliding surfaces, which can be occasionally reactivated after a very heavy raining period. These landslides are slow, so let's say that they tend not to threaten directly human life, but they can cause damage, let's say consequences to the built environment, such as for roads, for buildings, for all the assets. And when we talk about consequences, we are in the field of landslide risk framework. In this case, we can say that consequences can be the combination of the exposure and vulnerability. And usually the consequences are the outcome of the potential outcomes of the interaction of the given landslides with the environment, the built environment. Usually consequences entails the identification of the elements at risk and of the vulnerability. Elements at risk. The first group of things that we have to address are elements at risk, which can be identified over inventories, and most of all, according to the scale of the analysis, they can be derived. For instance, when we are talking about building, we can go from the aggregation of buildings when we move at small scale until, for instance, the single buildings when we reach the detailed scale. As for vulnerability of buildings and roads, in general, from the theory, vulnerability expresses the degree of loss of a given building or road when they mechanically interact with slow-moving landslides, in this case. And the vulnerability of the building, of the exposed road, can depend on the landslide type mechanism, of course, and its related intensity. The intensity of slow-moving landslides usually is associated with displacement or their velocity, but other influencing factor to the vulnerability can be also the location of the building or the road within the landslide body, or of course the structural characteristics, the construction characteristics of the road or the building. As for the intensity, when we talk about slow-moving landslides, generally in literature we are talking about displacement or even more sophisticated parameters such as differential settlements or angular distortions and so on. But usually these kind of data should be derived from conventional monitoring systems, but sometimes when we are working over large areas, this information can be not affordable in terms of cost and for the surveys. So that today, luckily, we can say that there is another technique from remote sensing, such as the differential interferometry, that is the processing of images acquired by synthetic aperture radar, which can provide today displacement over large areas of the ground surface with millimeter accuracy on the velocity. This technique always provides displacement information on targets that can be identified with the roof of the buildings, or with pipelines, bare rocks, and so on. That's why it has had huge exploitation in the last decades in the field of civil engineering. The study area. The study area that today I want to show you is located in southern Italy, specifically in Calabria region, and this area is a town. The name is Acri, with 20,000 inhabitants. The area of interest is this green area that is a deep-seated gravitational slope deformation, on which the exposed element in which we are focusing our interest, the Statal Road 660, crosses for around approximately, let's say, 3 kilometers. The area is affected by widespread slow-moving landslides. Indeed, the geological, geoenvironmental environment context is made by high-grade metamorphic rock of phylogenetic age. These metamorphic rocks experienced, with passing of time, intense weathering processes, which resulted in complex and deep weathering profiles, along which especially the sliding surfaces occur. As you can see from the map here below on the left, there are several landslides affecting the area. Especially they belong to the type of slide, debris flows, debris slide, and rock slide. And they are overimposed on a deep-seated gravitational slope deformation that you can see here also in green. The area has been studied for a long time by the National Research Council in Calabria, in Cosenza. With passing of time, different type of monitoring has been installed in the area, starting from, of course, ground-based conventional monitoring, such as inclinometers, which concentrated especially here in these landslide that is zoomed here on the right. That is an active rotational rock slide, which reactivated in 1998-1999, and then after that all these studies started. Then this inclinometer monitoring was integrated by GPS monitoring. You can see here the triangles with the location of the GPS, and of course piezometers, and more recently, this information were integrated by SAR interferometry. Going to the description of these four maps, you can see on the left there is the database of permanent scatters, which are points for which each of them we have a displacement time series, and of course velocity. These points belongs the ones on the right, on the left belongs to the Sentinel sensor, covering a period from 2014 to 2021. Images were acquired on both orbit, ascending and descending. The first on the top and the lower is descending. On the right, you can see instead Cosmos SkyMed images. Of course, you know that Sentinel images are acquired at C-band. Instead, the Cosmos SkyMed is acquired in X-band. That is much more fitting for this kind of application to the built environment. In fact, the Cosmos SkyMed images provided the maps of permanent scatter that you see here on the right. The points are located over, providing a good coverage on the road that you can see here in gray. And there is, of course, if you compare the left and the right maps, you can see that there is the density of the permanent scatter is much increased in Cosmos SkyMed images, which cover almost 11 years starting from 2011. The methodology, what we did, the analysis on the ACRI case studies were carried out following this methodology, divided in 4 phases. In the first phase, the main goal was the landslide characterization of all the landslides in the area. This landslide characterization was achieved by combining background information consisting of geological, geomorphological features, geotechnical soil characterization, landslides inventory map, and of course the use of ground-based monitoring network. At this stage, an important step was the comparison of the remote sensing data with the ground-based monitoring in order to assess their reliability, and it was a kind of validation which allowed us to use also remote sensing where ground-based monitoring was not available. In the second phase, starting from the map, the landslide inventory map, by merging with the urbanized area map, we singled out the exposed elements. For these exposed elements, in this case, we focused mainly on the road crossing the landslides, and in this road, the damage assessment was carried out with the use of archive photos, which were available from the National Research Council, field survey, and as a novelty, also Google Street View imagery was used for assessing the damage. After the assessment, the damage was ranked in a damage ranking scale, which we properly defined for the case study. And this allowed us to arrive to a multi-temporal damage classification. The level of damage was then combined with the intensity parameter in order to derive cause-effect relationship, which were deterministic cause-effect relationship relating the displacement with the damage. Starting from this and applying a probabilistic approach, we derive fragility and vulnerability curves till the estimation of risk. Now I will follow, I will give you also some other details about the methodology, then go into the results. First of all, we said that we had to, in the second phase, we had to define which was the damage severity ranking. The road was distinguished from the road pavement and the retaining structures, and we classified the damage first on the road pavement, going from D0 to D3, from negligible, let's say, to the severe damage, consisting, as you can see here on the photos, going from deformation, some cracks, and some dislocation of the road till the severe damage D3. Then, after the classification, a computation of the costs for repairing these different types of damage was computed, referring to a typical road with a width of 7 meters. Then moving to the retaining structures in the area, mostly consisting of gravity walls, L-shaped walls, or bulkheads. Also in this case, as you can see here from the map, from the photos, a different distinction of the level of damage was carried out. You can see here this bulkhead, which was tilted due to the displacement occurring on the road due to the landslides. Also, in this case, the cost of repair was computed, but in this case, just referring to D3, which was considered the reconstruction costs, because in the area we identified that indeed the repair to the structures was not carried out until it reached the D3 level. Another key step before going to the result was the comparison. We said the validation of SAR data with ground-based data. In this case, we compared the displacement derived from permanent scatters with GPS. On the left, here up, the first two graphs show the comparison of the velocity from SAR and GPS projected along the line of sight of the sensor. As you can see, both for Sentinel, the first two graphs, and for Cosmos Skymed, the second graph, we can see that the accuracy of the measurements from SAR data fall within this threshold, that is this gray strip that is among 1.5 to 2 millimeters per year, which is typical in literature. So after validating our data set from SAR data, we derived, first of all, these velocity maps with the projection operation of the velocity of SAR along the loss, from the loss to the slope. So you can see here the vector maps derived from Sentinel and Cosmos Skymed with the vectors colored according to their magnitude of the velocity. Then, for each one of the landslides, the landslides were associated. As you can see here, they were colored according to the velocity derived from SAR data. Then, all the information and the first goal of the phase 1 was achieved. The landslide characterization was accomplished in this map, in which you can see that all the landslides are clusterized, are typified, let's say, according to their typology. For the one that has the same depth, you can see we go from shallow landslides to the deep landslides, that is the biggest one, according to the, of course, the environment, the involved geomaterials and their velocity. This was the first step of the analysis, the first results, the landslide characterization. Then the second phase was more focused on the damage assessment. First of all, multi-temporal damage field surveys were carried out. During the damage survey, this kind of fact sheet was filled in which you general information about the road, about the landslides were collected, about the location of the road, the typology of the landslides, and also the description of the road. In this case, it was a primary road, a starter road, and the description of the retaining structure, the description of the state of maintenance of both the pavement and the retaining structure. And here you can see some photo collection of the same point, in which you can see that we have images starting from 2004 until 2005. 2005 till 2021. In this case, some photos were taken from the archives of the National Research Council. Some other one, the one, for instance, here in which you see the label SS, they are from Google Street View. This allowed us to follow the evolution of the damage on the road and or the retaining structure over about 17 years. From this, we derived, for collecting the damage information for all the damage section of the road, we derived this map of the damage of the road section. And here, the second map, in which the road is distinguished with the different stretches with the equivalent of damage of the retaining structures. By putting all together this information all together, we got these different multi-temporal damage maps, starting from 2008, 2011 until 2021, in which the road is colored according to the level of damage which was recorded on the different stretches of the road. This is again the map of the road. You can see here, this is the road track covered by permanent scatterers. Then at this stage, around each damaged section of the road, this is the road, the damaged section, the number of PS was computed following within a buffer of 10 meters. Within this buffer, the velocity were first of all projected along the slope, and then they were averaged. So each one, for each section, we derived an average velocity, which was multiplied by the time to get the cumulative displacement over 3 years. In this case, you can see here in this histogram, you can see the track is a section from A to B along the road track, in which the cumulative settlements are represented. And as you can see here, we have the most active portion of the rock slide is this one, following within this first step, more closer to the Acre municipality. Then for each section at this stage, we had the level of damage and the intensity parameter, which was the cumulative displacement. These information were collected within this diagram, in which you can see that each star represents a section of the road which with its own damage recorded and the cumulative settlement that was derived from SAR data. As you can see here, we see that as the cumulative displacement increase, also the level of damage increase. Then from this diagram, it was derived on the right a frequency diagram, in which you can see that distinguishing in different ranges of the cumulative displacement, you can see that with the increase of the cumulative displacement, of course, we have the lowest level of damage decrease and appears the highest level of damage. Then, as noted as it is well known in literature, from this map, it was possible to derive an empirical fragility curve by applying this formula, that is the log normal distribution function, in which you have the empirical fragility curves which relate the level of, for each cumulative displacement, they associate the probability of reaching or exceeding a given level of damage, in particular the three levels of damage that we considered, D1, D2, and D3. Then from fragility curves are started to be used in seismic engineering, and then more recently have been also mutated to landslide risk. From fragility curves, also vulnerability curve can be derived from by applying this formula, in which that is a kind of weighted damage, weighted on the probability of occurrence derived from the fragility curves. This curve relates, for if you enter this curve with a given displacement, you can get the expected level of damage. So, and in this case, the real data that are these circles were fitted with a tangent hyperbolic function. The vulnerability curves was used in this research also as a forecasting tool. How? Indeed, we noticed that we were informed with the more long-term study. We understood that in the area, the repair to the street, to the road, were carried out at maximum every 3 years, so that with the assumption that the velocity of displacement was kept constant over 3 years, we multiplied the velocity by 3, and for each scroll road section, we were capable to compute the cumulative displacement in 3 years. So entering the curve for each section, we derived the expected level of damage that in 3 years should be expected to the road section. And by collecting all the information, we derived this map, in which you can see the road track, which is colored according to the expected level of damage in by the end of 2024. As you can see, by the end of this year, most of the road is expected to get a severe level of damage if no countermeasures are taken. From this information, of course, it was also possible to make a comparison, because also on the cost for repair, so that is the third risk associated to landslides in this case. And it is interesting to note that if no countermeasures are taken in these 3 years, the expected damage loss, economic loss in 2021 was around 120,000 euros, whereas by the end of the 2024, the expected level of damage is more than 4 times. It's around 500,000 euros. Most of all because in these 3 years, it was computed that most of the retaining structures, if no countermeasures are taken, will get to the highest level of damage, which usually requests for a repair in order to not have the road blocked, stopped for the circulation for a given period. So this was a way to use SAR data for within probabilistic tools that are the fragility and vulnerability curves, in order to reach risk estimation, also quantitative risk estimation over 3 years of forecast. So going to the conclusion, we can say that in our study, we developed a quantitative risk assessment for road interacting with the slow-moving landslides, and the novelty was here the combination of SAR data, remote sensing data, but also Google Street View imagery, in order to get on one side this cumulative displacement, on the other side information on the evolution of damage that indeed represents the interaction of the road with the landslide body. Another important step was considering the road as a whole, not only the pavement, because in the area the pavement is more easily to be repaired than the side retaining structures, which are more repaired just 5 times every 3 years. Then the reconstruction of the damage evolution, which was related to the cumulative displacement in over 3 years. Of course, these are the tools that can be more and more tested, but indeed they could provide, especially for expeditive analysis, because the aim was to identify which were the section of the road which in 3 years may reach a level of damage that is no more acceptable, and on which the prioritization of costs of money should be addressed. Thank you for your attention. Here you see my details. Of course, there is also my mail, and I will be happy to answer to your question or any contact with you and with all the audience. Thank you.